إذا كررت هذه العملية بعد أشهر
السلام عليكم. حاب احكي لكم اليوم شوي عن تجربتي في الريسيرش وكيف ممكن انه تشوف اذا انتم حابين. هذا الكاميرا hopefully انه شغال. زي ما قلت حاب احكي لكم عن ريسيرش تبعي، كيف بلشت، ايش الريسيرش، وممكن يعني الواحد يشوف حاله اذا interested في الريسيرش ولا لا. اوكي، طبعا يعني مش كل اشي هو ريسيرش، بس الريسيرش يعني هو اللي بيعمل خلينا نقول تطور للمجتمعات بالاضافه لاشياء ثانيه. اوكي، انا راح احكي اليوم عن nature inspired control systems. اوكي، وراح احكي لكم شوي كيف انه nature is important بالنسبه للريسيرش. اوكي، تكون البرزنتيشن بالانجليزي، حدا عنده مشكله فيها؟ اوكي، alright, so let's start. What is research? Okay, research is exploring an idea that has the potential to do something. Okay, you have an idea. If that idea has the potential to maybe solve a problem in general, problem in the community, problem in science, problem in math, okay? If you have an idea that might solve a problem, then you have to start research. Try to find how we can solve the problem, what techniques you have, and how you can approach this problem. And maybe through that you might come up with new technology, solve that problem, okay? Or maybe if you use the current technology is limited, so you might want to enhance it, okay? So you do research for that purpose, and then you might develop a new application or product, which is the most important thing. At the end of the day, you want something that benefits the community. Okay. Most important is that research is problem driven. You don't start thinking, okay, I'm going to do research and try to find something to research. No, actually you have to look for problems first and then do research to solve these problems. Okay, or you have an idea for a new product and then that should be the start. Okay. Now, research and discoveries. This is not supposed to be here. Anyway, now there's a slight difference between research and discoveries. Okay, you do research to discover something. You might end up with a discovery or not. Okay, for example, penicillin. You know who discovered penicillin? Sir Fleming. He was doing research, and it was purely by accident that he's discovered this penicillin material, which became a vaccine. Okay, and that was a discovery. Okay, it was a byproduct of research. Okay. Discoveries deal with things that exist in nature. Okay, you don't develop a discovery; you just discover it. It's there. It's waiting for somebody to find it. Okay, and then find a use for it. Okay, for example, electricity. Who discovered electricity? Okay, many think that it's Benjamin Franklin, but it was actually discovered years before that. It was the first record of electricity was 600 BC. Okay, the new names that surfaced, Ben Franklin and others, they just discovered how to use it, how to channel it, how to make it useful. Okay, Ben Franklin just did an experiment. He flew a kite, connected to a key, and proved that lightning is electricity, and you can have a current flow out of it. Okay, but the first battery, this was discovered in an area near to Baghdad in 1930, and this dates back to approximately 700, to the year 700, and it's thought that this might be a battery because it connects, it consists of some copper layers with iron rod, and they tried to use it as a battery, and actually they were able to generate electricity out of this. So those discoveries are made years and years ago. There's supposed to be here something, but anyway, now research is important. That might lead to discovery, but not necessarily. Okay, discoveries usually they make you famous. Okay, that's the only thing. Everybody knows your name. Okay, and then somebody else has to come after you and then use that discovery, do some research on it to come up with something else that might be an invention or a product, an innovation. Research may lead to inventions, not necessarily. Okay, many people do research, but don't be frustrated if at the end of the day you did not come up with something that people are directly gonna use. Okay, it's research. Anything is possible. Research led to the invention of light bulbs. Okay, electricity was there, discovered, and then they came up with this product. Inventions change our life. Okay, discoveries and research. Scientists know about discoveries and research. Okay, they value that. The general public does not. They don't know about it. But when you come up with an invention, at the end of the day, people will start using that invention, and then they will start to recognize you because you changed their life. And many inventions, they don't make you famous. Nobody knows who invented this or that most of the time. Okay, the most important invention was the wheel. Okay, imagine your life without a wheel. Okay, nothing's gonna happen. Okay, engines. Okay, that's how you generate electricity. That's how you generate motion. Those are the most important inventions in our lives. We use them just for granted, but think about your life if it wasn't, if those inventions were not there. And most important is that inventions, if you invent something, you become rich. Okay, but you have to be lucky there. Now, how to do research? As I said, first you have to find an idea to research. You have to develop an interest in an idea. Okay, and then you have to search all the existing knowledge in the literature everywhere. Okay, you don't want to start research and then end up with something that somebody did years ago. Okay, you have to find where the state of the art is, okay, before starting your research. And then you have to study and understand all the current technologies. Okay, you want to build on them. There's a saying, don't reinvent the wheel. Use what is available and then start from there. Look for problems, bottlenecks, and drawbacks in existing technologies. That's what we want to research. Okay, where the technology stopped and what's the problem in that technology, and that's where you start your research. set your target, what you want to do, choose the methodology, how do you want to tackle this problem, modeling, mathematical, experiments, trials, all that, and then try all new approaches, technologies to solve this problem. Try everything. Okay. And then, most important, you have to observe what's happening. Okay. Compare your results with others. Okay. See if you are going in the right way. Of course, after that, you have to restart. Nothing happens the first time. Nothing works the first time. Okay. You have to try again and again. Okay. So you have to try, restart, and maybe you might end up with results, but not necessarily. Okay. Many research just reaches dead end. Okay. And that's a result by its own. Okay. I know a friend who did a PhD. He started his research. He worked on his research for over 3 years, and they could not come up with a result. And that was the result in its own. He got his PhD. He proved that this problem cannot be solved. Okay, and that was a result. Okay, so if you reach no result, just be happy and start something else. Okay, and then you are a real researcher. If you don't, okay, then and you give up, you're not a researcher. Try something else. Okay, now if the problem is solved and you got results out of your research, okay, you're just lucky. Okay. As I said, results are not guaranteed. Okay. Now, you want to know if you are into research or not. Okay, not everybody can be a researcher unless, okay, you have some characters. For example, you have to love and value life. You want to be part of this life and improve it. Okay. You have to be curious how things work. You have to study everything, try to play with everything, break everything, and see what's inside, how it works. Okay. Look for cons, not pros in things. Okay. You have to look for the problems around you, not the things that are going fine. Okay. You should have passion and don't give up. Okay. Researchers do not give up. You have to have sharp eyes. Things happen in a blink of an eye. If you are doing an experiment, something might happen, and it might happen over less than a second. If you are not observant, you don't notice things. Okay. It just might skip and you would not notice it. Somebody else will. Routine. Researchers hate routine. Okay, and that's a good thing, because in research there's no typical day. Something new happens. Okay. Not necessarily smart. Okay. Don't think that researchers are smart. Okay. Just consistent, and but definitely not stupid. Don't think about money, because most researchers are poor. Okay, unless you invent something, then you're lucky. Now, back to our topic. Why nature-inspired research? Okay, many of our problems have solutions. They're out there in nature. You just have to look for those solutions and see how they work in nature. Okay, and try to mimic nature. Try to find a way to solve your problem just like nature did. Okay, before we learned how to fly, before we designed the first airplane, people looked at birds and started to see how the bird wing is shaped, why this bird flies and why that does not fly. Okay, and then that's a solution. You try to research that solution and see how you can develop technology that mimics that works the same way. Okay, for example, Also, bats are blind, but they find their way just fine in the day and in the dark. Okay, that's a solution that we might use. That's a technology that might benefit us. Okay, we don't see in the dark. Okay, that's how they came up with the radar and many other ideas, sonars. Okay, the same idea, ultrasounds, ultrasonic waves. Okay, that came up from nature. Nobody actually researched it and, oh, I can use this. No, actually, nature is using that, so let's use it. Okay. Ships. Okay, the old days, you all know the ship has a pointy nose. Okay, sails in water, but you need huge power, huge propellers and engines to push the ship through water. On the other side, this nice fellow is heavy, okay, and travels at very, very high speeds. You'd be surprised. And yet it has a round nose. But it sails very smoothly in water. Then somebody nosy thought, hey, let me experiment with that. Let me research that and see why this guy is traveling easier than our ships. And it turned out that round objects travel better in water than sharp objects. And that's why new ships, they all have this underwater submerged nose bulb. All new ships, you don't see that because it's underwater. It's the part that's submerged in water that you want it to be round. The above water part can be sharp. That's just fine. Okay, and I don't know if you noticed in this first picture. Did you notice something here? This guy over here, he is actually standing on the nose of this ship. It does have a bulb, but it's submerged underwater. And this is just the tip of it. Okay. All ships have that. Now, I'll talk about my research just quickly. I work with control systems. Okay. I'm not a control specialist. Okay. My knowledge in control is just limited, so you don't have to be an expert in something to research it. Okay. When I was at school, the worst class I had to go through was control systems. It was absolutely the worst. Okay, and I thought, okay, I'll just pass it and I'll never see it again. Okay, it never happens. It's not like that. You don't know the future. Okay, so that's why you have to concentrate in all classes, whether you like them or not. You never know what's going to happen in the future. All my work before that was in machine design. That's what I had in mind. I was going to be a machine designer for the rest of my life. Okay, but it happened, and when I started my PhD, I had an opportunity to work on the control of ship-mounted cranes. Those are cranes that are on ships. Most commercial ships have cranes on them. And there's a problem with those cranes that if the ship starts to rock, roll, and pitch, the cargo lifted by those cranes will start to swing. And if it starts to swing, you can do nothing with it. You cannot load it or unload it from other ships. Those crane ships are usually used to transfer cargo from container or big cargo ships to smaller ships. Okay. But if the load starts to swing, then you cannot actually control it. You cannot deposit it on the other ship. So that was the problem I had to research. Okay. So I decided to start using computer simulations. Okay. I built a computer model, a simple 2D computer model of a ship with a crane and payload attached to it, and started to simulate the ship motion and see what happens to the load. Okay. I stared at this simulation for days, and then I thought, okay, the tip is moving a lot. Okay, let me try to move. This is what it's called, the boom of the crane. Let me try to move it in an opposite direction of the ship motion. Okay, so that I minimize the motion of the tip, and then maybe the load will start swinging. And I did that, and it stopped. And I was really happy, because that was the 4th week after I started my PhD. So that was I was done. Okay, and then I looked at the results. I plotted the motion of the tip of the boom. Okay, and I noticed something, that the red line, the boom was supposed to move according to my theory, to move in an opposite direction to the ship. According to my theory, it was supposed to move along the red line. But when I plotted the actual motion of the boom, it turned out that there was a little shift over here. Okay, there was a little delay. So I thought, okay, with this delay, the results were extremely beautiful. Then I will try to design a better controller so I can eliminate this delay and have both lines exactly on top of each other. And I did that, and the system crashed. Okay, so, all right. So what happened? All right. It turned out that this delay is what made the system work. Okay, you have to, as I said, be observant. Don't let anything just pass by without studying it. It turned out that this delay is what made the system work. So I started playing with this delay, researching this delay. Okay, how much delay do I need? Which delay is better than the other? Okay, so I started to do many simulations, increase the delay, and maybe increase the percentage of the motion relative to the ship. And after many simulations, I found out that, okay, this is the best region. This is what gives me the least payload swing. So it turned out that a delay of quarter of a period of the swing is the best, but that's too many details. But that's how you work your research. Okay, you notice something, you take it and study it from all aspects. And we came up with what's called delayed feedback controller, and it's already has been patented and everything. Now, after you do the simulations, you have to run the experiments, because simulations are usually designed in ideal, let's say, environment. There are many things in real life that you cannot really simulate. So you have to build an experimental setup and test it experimentally. It's not going to work the first time. Okay, so you have to tune it and work on it further. So we built a ship simulator. It's just a simple robot, basically, that simulates the ship motion. Okay, and we built a little crane similar to the one installed on ships, and we found the same swing that we saw in the simulations. And then we used the same controller and applied it to this crane, and it just worked. Obviously, it did not work the first time. Okay, it took months to get it to work. Okay, and it was perfect. Now, research does not stop there. You got an idea that worked, beautiful. Try to find another application for this idea. Okay. Quayside container cranes. Those are the big cranes that unload and load containers from container ships to ports to trucks and the other way around. Okay. These are the key of advanced industry. Okay. There's a problem there. An average ship, I wouldn't say a large ship, an average ship carries 4,000 containers. New ships carry up to 22,000 container on a ship. Okay, it looks like there's a pile of 7 containers here, but actually there are containers in the ship more than there are on the ship. The problem is that this guy, the operator of the crane, is sitting up here, and he is 45 to 50 meters above ground, and he needs to move the container and drop it on a truck, and the margin of error that he has is a maximum of 50 millimeters. 50 millimeters, and this is where you are. Okay, 50 meters above ground. Okay. So what happens is he has to slow down. He has to be an expert. They train for 10 years on smaller cranes before they are allowed to touch this crane. So the problem is they have to start slow, end slow, and then try to find the truck, slow down, okay, and then try to correct the location, the position of the container slowly until you are able to unload it on the truck. That's a lot of wasted time. Okay, we're talking about an average ship of 4,000 containers. Think about 10 seconds in each container. That's a lot of time. Okay, so now this is another smart guy. He tried to be a little faster, and he broke the truck. All right. So I took that controller that I designed for the ship-mounted crane and tried it here, built an experimental setup, okay, and watched what happens if I run the crane without controller. And obviously I will get swing in the container, okay, because I'm not an expert, just like that crane operator. But then I installed the controller on it, and this is what happened. The same motion, a little faster with the controller, and no swing. All right. Have to try many cases. Maybe you're lucky the first time. You have to be sure that you're lucky every time. Okay. So here's another case. And it was really successful. Nice. Well, so what's the next step? Next step is try to find the crane to test the controller. Okay, this crane is approximately $40 million worth of money, and it works 24 hours a day. So it's hard. Nobody in his right mind will give you a crane to test your controller, and the daily income of this crane is $25,000 at least. Okay, but finally, after years, we found one. Okay, and installed the controller, and it worked after 8 months of trial, because a lot of things that we did not have in the lab showed up on the real system. Okay, you'll be surprised. For example, the least is, in the lab, we installed sensors on the cables that are carrying the load, and it went fine, and we worked on it for years and nothing happened. When we did that on this crane, the cable is 30 millimeters in diameter, and it's very rough, and within 2 days it went through the sensor, it ate the sensor and finished. The sensor was destroyed in 2 days. So it turned out we didn't see that in the experiments. So we had to design new sensors that can resist this cable. Okay. Now we were able to save 11 seconds in every move. over the most experienced operator, which is very nice because 11 seconds times 40 times 4,000 containers, that's almost a day of work. Okay. Ships usually in busy ports, sometimes they have to wait for months outside the port to wait for their time or for their for a chance to get into port and load and unload. Sometimes they spend up to 6 months. Those ships you see in the horizon, they're not having lunch over there. They're waiting for they're in queue. All right. The hardware is simple. There's not a lot of problems. It was a simple box installed in the crane with the electronics programmed using a computer software. It's important if you are a researcher, you have to learn all this. Don't have much time, so I will just go quickly over another research that I was working on. Control multi-mode systems or multi-body systems. If you have a system that has more than one component and they all swing, how you can do that. Okay. I use the same controller. The regular controls, they deal with one frequency. Okay. It was nice, but there was still swing. The large motion was eliminated, but the other swings were there. Okay. There was a theory that if all the frequencies are multiples of each other, then one controller works for all. But the problem is frequencies in general are not multiple of each other. So I was in control class, actually, control 101, the first class of control. I was explaining to my students that, okay, this is the basic theory of control. If you have a system and you add a feedback to the system, the only thing that happens is the frequency changes. Okay, and that was a class. Then, okay, I stopped there and went back to my office. My problem in the previous experiment that frequencies are not odd multiples, and I have a problem there. So what if I can benefit from this and change the frequencies of the system so that they become odd multiples, and maybe then the system will work. Okay, and that exactly what happened. This was a single frequency, and here's the system after using feedback to adjust the frequencies to become, and just came like this. Okay, as I said, you have to observe everything. Okay, don't let anything just pass you. Okay, that's an idea that just came out of nowhere. Okay, and we used it. All right, and came up with a solution. And we are now working with some of my friends on how to expand this idea to beams or solid structures like wings. Okay, there's a huge problem in wings and aircraft, which is called flutter. Sometimes the wing starts to just vibrate like this and might break, and that's why aircraft wings, they have very, very solid and heavy base. If you can eliminate that heavy base, you can carry more. Okay, and we're trying to go a step further in our research to control this, eliminate this swing. So, in conclusion, keep your eyes open. As I said, things are quick. Question everything. Okay, you have to understand how everything works. Choose the topic that you want to work on. Okay, don't let somebody tell you what to work on. Okay, you have to have passion for that topic. Learn many research tools. Don't say, okay, I'm a mechanical engineer, but I know a lot about electronics. Why? Because I have to use electronics. Don't be a slave to somebody else. Okay, here's my friend. He knows electronics, but he's not always available. You have to learn everything. Everything that you can use, you have to learn it. Softwares and everything. And research should be a hobby. You have to love research. It cannot be a job. Okay? And that's it. Thank you. Questions?
Not in questions of website, maybe like of user experience. And I have questions? Yes.
Simulation programs. Show me. Excuse me.
Okay. Now, you have many softwares available for simulations. Actually, I used here two softwares. You can use MATLAB to run simulations, and actually MATLAB, if you are familiar with it, you can plot, draw, and generate even animations. Those are the boom crane, the ship-mounted crane animations. They were generated using MATLAB. But there are a lot of other simulation softwares that you can actually use to generate those simulations.
Quick question, last one. Anybody? Yes?
This relates to the way that the boat rocks and how you were able to register the frequency.
Mm-hmm.
Sometimes it changes, like
Yes.
the way the boat rocks isn't constant, so it's not.
Yes, exactly. So you have to have a sensor on the ship, what's called a tilt sensor, a sensor that measures the angle of swing of the ship. Okay, and then you have to use that data online. It has to be continuously monitored, and based on that motion, then you have to design your controller. I don't know if I can go back. Let me just show you something very quick. Here, over there, we have a sensor that measures how this platform or robot is moving. That's how we design the controller to work. All right?
بقدر أسأل سؤال ثاني؟
Sure.
السيميوليشن اللي اشتغلت عليها كانت inspired من شو من النيتشر؟
Okay. Really بالنسبة لهذا عمرك شفتي ولد بيلعب بيويو؟ alright. لما بيرمي اليويو بتنزل ستريت، واكشلي مرات ما بتنزل ستريت، هو في عندهم حركة هيك بإيدهم بيعملوها بتوقف. Right? So that was يعني I was watching a little boy doing that، وحاولت أتعلم كيف بيعملها. جبت كرة وعليها سترينج وقعدت أعمل زيه، أرمي الكرة وأشوف سوينجز، أجرب لغاية ما تعلمت كيف بيعمل. لقيت حالي عم بعمل موشن. I thought بالنسبة بالنظر هيك بين إنه أنا عم بلحق الكرة over the football، الكرة هاي exactly. بس actually الاشي اللي عيني ما لقطته إنه أنا كان في ديلي بين إيدي وبين الكرة، وهذا الديلي اللي بين عنا في الإكسبيرمنتس. actually زي ما الكرين، الكونتينر كرين كان بس اكستنشن لهذا الريسيرش. اوكي، انه انا عندي كنترولر عملته لهذا النوع من الكرينز، ليش ما اجربه على اشي تاني، كرينز تانية. في many types of cranes جربناه على كمان على الكونستراكشن كرينز اللي بتشوفها على المباني. سو يعني لما بتوصل للريزلت مش هذه النهاية. ما هذا اللي كنت بحكيه انا هلا، انه بالنسبه للكره والهذا، لانه انت ريلي مش الكرين هو المهم، انت المهم هو هذا البارت، الكيبل واللود، هذا اللي بنحكي فيه.
هلا لما تسوي اكسبيرمنت وين تروح حتى تعمل هاي الاكسبيرمنت؟
انت لازم تعملي هلا يعني اكيد لازم الواحد يكون في ريسيرش فاسيلتي، في فاند افيلبل، بده هو لازم يعمل. يعني الاكسبيرمنتس اللي انعملت هذه it was all our design. يعني احنا بنعمل ديزاين للبيس وبنعمل ديزاين لكل شيء وبنجرب. you have to learn.
Thank you, Dr. Arif. Thank you all for coming.
شكرا.